All right, so now we're going to specifically talk about a type of reaction that we've sort of discussed before, but we're going to go more in depth, and these are acid-base reactions. Okay, so an acid is a compound that produces hydrogen ions in aqueous solution. We also call these protons because hydrogen consists of one proton and one electron. So when it loses that electron, it's referred to as it's just a proton that's left over, right? So sometimes hydrogen ions are referred to as just as protons. What we're going to see is that these acids are thus like ionic compounds where the cation is hydrogen, right? So for example, HCl, this is going to be an ionic compound that consists of a hydrogen ion and a chloride ion, right? This would be what we call a monoprotic acid because mono meaning one, it has one proton that it can donate. Sulfuric acid, H2SO4, also has donatable proton. It actually has two, so it would release two protons, right? So this is what we would call a diprotic acid. And then phosphoric acid has three hydrogens, so it's a triprotic acid. Okay, so that's what acids are. They are compounds that have a hydrogen ion. A base is a compound that produces hydroxide ions in aqueous solution. Okay, so most bases and the ones that we're going to kind of focus on are hydroxide salts, right? So sodium hydroxide, if you take that sodium hydroxide and you dissolve it into water, the sodium and the hydroxide dissociate, and so you get these hydroxide ions in solution. Okay. We also have acid. There's like this Bronsted-Lowry definition of an acid and base that's really important. So a acid is something that donates a proton. Also, again, remember a proton, by that I mean a hydrogen ion. And in contrast, a base is a compound that accepts a proton. So hydroxide ions, those basic ions, they will accept protons. Other species as well will accept protons. So in this example here, we have ammonia playing the role of a base and hydrochloric acid playing the role of an acid, right? And what the base is doing is the base is accepting a proton. So notice that I go from being H3 or NH3 to NH4 plus, right? It's accepted a proton. So not only does it have an extra hydrogen, but we got to conserve our charges. So that positive charge also came with it. And then the hydrochloric acid, the acid is the one that donated a proton. So I go from having my hydrogen here to now I'm missing my hydrogen. And again, it left it as H plus. So again, conservation of charges. It will leave behind the chloride ion, Cl minus. Okay, and I keep on saying this conservation of charges. Basically, this side of the reaction has a net charge of 0. And so this side of the reaction has to have a net charge of 0 as well. Importantly, an acid, once it donates a proton, its charge will decrease by 1. And a base, once it accepts a proton, its charge will increase by 1, right? So ammonia started out being neutral. When it accepted that proton, it had a positive charge. Our acid started out as neutral. When it lost that proton, it took on a negative charge. Okay. These definitions, so I said like play the role of an acid, play the role of a base. This is something that I think is kind of confusing to students at first because we have things that we consider acids. Hydrochloric acid, it's got acid in the name, right? being an acid in terms of like where, that's kind of like the category of where it is in the stock room. You'll have a shelf full of acids. All right. In a chemical reaction, though, we are talking about things that play the role of an acid and play the role of a base. Water, for example, can play the role of both an acid and a base. So you don't want to think about it within a particular category. This substance is always this. You want to think about what it's doing within the reaction that's in front of you. If it's accepting a proton, then it's a base. If it's donating a proton, then it's an acid. That's the role that it's playing within a chemical reaction. All right, and we'll see what I mean by this right here, right? So hydrochloric acid will react with water to form a hydronium ion and a chloride ion. Again, the acid is an acid because it donates, right? Or loses it, right? It loses it to its partner. So we see that this hydrochloric acid went from having this proton over here to having lost it because it donated it, right? So where did it go? We went from being H3O or H2O to H3O plus, right? So again, notice those charges. My acid lost a proton, and so its charge decreased by 1. My base gained the proton, and so its charge decreased by 1. So water in this reaction is playing the role of a base because bases accept H plus. So in all acid-base reactions, there will be something playing the role of an acid and something playing the role of a base. Something will be donating a proton, that's the acid, and something will be accepting a proton, that's the base. On the other side of the reaction, we have this new terminology that we have to learn here. Our acid, after it donates the proton, becomes what's called a conjugate base. Okay, so after an acid donates its proton, we call it a conjugate base, the conjugate base of that acid. Likewise, a base, once it accepts a proton, it becomes a conjugate acid. Right, so all acids have conjugate bases. Those are just the form after it's lost the proton. And all bases have conjugate acids. That's the form after it's accepted the proton. Okay. If we go on to this next reaction here, now we have ammonia, which we said is a base. So it's going to accept a proton. So it goes from being NH3 to NH4, and now has a positive charge. Each base, we said, has a conjugate acid. That's the form after it accepts the proton. Right, so just notice the difference between our base ammonia and its conjugate acid, the ammonium ion. And then in this reaction here, we had water playing the role of an acid. Water is what's donating that proton, right? I go from being H2O to having donated a proton, having lost a hydrogen, and now also having a negative charge. So water plays the role of the acids. So the hydroxide ion here would be the conjugate base. Right. So again, we have things that we think of as acids. We have things that we think of as bases. We kind of put those compounds in a certain box, right? In a category. But when it comes to acid-base reactions, you want to take a step back and ask yourself, who's playing the role of an acid? Who's donating the proton? And who's playing the role of a base? Who's accepting the proton? Because we have certain species that will do both, right? And so water in this first reaction was playing the role of the base, but in the second reaction, it was playing the role of an acid. So we can't think of water as either an acid or a base. We want to look at the particular reaction and think about the role that water is playing in that reaction. Okay, and make sure that you understand how to go from your acid to your conjugate base. You're losing a proton, right? Whereas if you go from a base to the conjugate acid, it's gaining a proton. Okay, so let's practice that here. What would be the conjugate base of HNO3, right? Nitric acid. Well, so if it's asking me for the conjugate base, that means that this is the acid, What do acids do? They donate protons. So to go to the conjugate base, I'm going to have to lose that proton, so NO3, and importantly also decrease my charge by -1. So an acid going to its conjugate base loses a proton, loses the hydrogen, and its charge decreases by 1. All right, so I went from being neutral to having a charge of -1, and I lost that proton. All right, so let's now go to our next example. What is the conjugate acid of O2-, the oxide ion? So I'm looking for the conjugate acid. That means that this is playing the role of a base, right? So going from base to conjugate acid, what do bases do? They accept H+, and in the process, the charge increases by 1. So I'm going to have to add a hydrogen, right? Because that's what my base did, is it accepted a hydrogen. And I have to go from a charge, I have to increase my charge by 1. So I go from being a charge of -2 to -1. Okay. What is the conjugate base of H2SO4? I'm sorry, of HSO4-. So that means that this is playing the role of an acid. Remember, acids will lose a proton, so I got to get rid of this here. So I'm just left with SO4. And then my net charge is going to have to decrease by 1. So I go from being -1 to -2. What is the conjugate acid of HCO3-? Well, if I'm looking for the conjugate acid, that means that this is playing the role of a base. A base accepts a proton, so I'm going to have to add a proton. So this becomes H2CO3. And then I have to increase the charge by 1. So I go from having a charge of -1 to being neutral. Okay, so this would be the conjugate acid of this particular base. All right. Now, last problem we're going to do is, given a chemical reaction, we're going to label the species as acids, bases, conjugate bases, and conjugate acids. So again, what are we looking for? What's the definition of an acid? You really need to have this kind of ingrained in your brain. An acid is a donator, donates H+, and a base accepts H+. So looking at, we can just take it one at a time here. HF, find the counterpart on the other side. That's just F. Did it donate a proton or did it accept a proton? So in this case, the hydrofluoric acid plays the role of an acid, and the fluoride ion is its conjugate base. Okay. Likewise, in this case, we see ammonia. Follow that on both sides, and we can see that it has accepted a proton. So this ammonia plays the role of the base, and the ammonium ion is its conjugate acid. Okay. Let's look at the other one. We have this. Let's just say that this is what's called an acetate ion, but let's say that we don't know that, right? So it doesn't really matter. What's important is find it on both sides of your chemical reaction. So here it is over here. Here it is over here. And what are you going to ask yourself? Did it donate a proton or did it accept a proton? In this case, it goes from having a negative charge to now being neutral and having this extra hydrogen. So it played the role of a base. It accepted that proton, and that makes this its conjugate acid. So we don't even really have to know what this is, what this molecule is. We just need to tell what role it's playing in this particular reaction. Likewise, I have water. I know that water can play the role of an acid or a base, so I got to pay attention to what it's doing in this reaction. Here, it's going from being H2O to being the hydroxide ion, so it lost one of those protons, gained a negative charge, so it's playing the role of an acid, which makes this its conjugate base. Okay. The last thing we're going to talk about with regard to acid-base with regard to this particular lecture is specific to water. We talked about how water can play the role of both an acid and a base, right? We saw that in several reactions that we looked at. So it turns out that water, when you have a sample of pure water, it's actually reacting with itself, right? We can have water play the role of both an acid and a base, so it's going to react with itself. One species is going to play the role of the acid and donate the proton, and the other one's going to play the role of the base and accept the proton, creating this this sample of hydroxide ions and what we call hydronium ions. Right, so this is happening in water. Remember, we talked about acid or equilibriums last time, right? So although this reaction is happening in this forward direction here, going to products, it's also always happening in the reverse direction. We talked about equilibrium constants, products over reactants. And we see that the equilibrium constant for this reaction is really, really small, right? So it doesn't favor the products very much. Nonetheless, there's always a little bit of that, of both hydroxide ions and hydronium ions in solution. And they're always in this perfect ratio where the concentration of hydronium ions times the concentration of hydroxide ions is equal to 1 times 10 to the negative 14. This is what's sometimes referred to as the kW of water. All right. Now, if you might be asking yourself, I thought that reactions, equilibriums were always products over reactants, right? So that would look similar to this. But I should also then have my reactants on the bottom. But because this is taking place in solution, solutions are primarily water, right? Because of that, this value right here, no matter what you do with it, whether you add acid or base, you might change. If you added acid, you would increase this concentration, but you're never going to change the concentration of water. This right here will remain constant, which is why we just leave it off of our reaction equilibrium altogether. Right? You could put it in there. You would just always be putting in the same number. It's about 55 molar for a solution is usually the concentration of water. So because of that, they just leave it out altogether, kind of combine it in. And so we can say that this is what we're going to have in our head for water. Okay. Now, adding an acid would increase the concentration of this and decrease the concentration of the hydroxide ions, because the both of them combined have to always equal 1 times 10 to the negative 14. Likewise, if we had a base, we would see that that increases the concentration of hydroxide ions, but in order to compensate, the hydronium ion concentration would decrease. Okay, so the concentration of hydronium ions in stomach acid is 0.1 molar. Calculate the concentration of hydroxide ions. Well, we're going to use this relationship where we know that the concentration of hydronium ions times the concentration of hydroxide ions is always equal to 1 times 10 to the negative 14. You have to have this memorized for the ACS exam. They will expect you to know this. You will not be given this formula here. So my exams are all about mimicking the conditions of the ACS exam, so I'm also going to expect you to have this memorized. Okay, So what we're going to just do is plug in our variables. So what's my missing variable is this hydroxide ion. I have my hydronium ion concentration. I have that Kw value, that 1 times 10 to the negative 14. So I'm going to rearrange this equation by dividing both sides by the hydronium ion concentration. Over here, that will cancel out. So I'm just going to erase it. And I'm left with this expression where the hydroxide ion concentration will be equal to that Kw, that 1 times 10 to the negative 14, divided by the concentration of hydronium ions. So now I can just plug in what was given to me in the problem, which is that the concentration of the hydronium ions is 0.1 molar. Oh, sorry, this would be 10 to the negative 14. I was jumping ahead. Because once I punch that into my calculator, I would see that my answer that I got was 1 times 10 to the negative 13. This is equal to the hydroxide ion concentration in the stomach, right? So these problems are all about the fact that any aqueous solution will always maintain this balance of hydroxide ions to hydronium ions such that their product is always equal to the same value, that 10 to the negative 14. Okay, as we discussed with equilibrium constants, they're specific to a temperature. So this value corresponds to a temperature of 25 degrees Celsius. You can just assume that all these problems are going to be at 25 degrees Celsius. Okay, one other thing I want to point out is that a sample that we consider to be neutral, which is pretty much what you would get if you took the water from the tap at your house, is when the concentration of hydronium ions is equal to the concentration of hydroxide ions. And you can do the math and convince yourself that they would both then have a concentration of 1 times 10 to the negative 7. So this is what we would consider to be neutral water. It would be considered acidic if it had a greater concentration of hydronium ions. So acidic, let's actually put that down. Acidic means that the hydronium ion concentration is greater than that 1 times 10. I'm not even going to write the 1. It's kind of pointless. Hydronium ion concentration is greater than 1 times 10 to the negative 7, meaning that the hydroxide ion concentration is less than 1 times 10 to the negative 7. And likewise, basic conditions, let me actually write this over here. Basic conditions would be when the hydroxide ion concentration was greater than 10 to the negative 7, and the hydronium ion concentration was less than 10 to the negative 7. Those would be basic conditions.